Hi guys. Hi guys, welcome to enginerdmath channel. So we're live. Our topic for today is finding inverse Laplace transform part 2. So I already have a previous video, part 1 for this topic, finding inverse Laplace transform. So if you haven't watched that yet, I will just put the link on the description. Also, I already have previous videos all about Laplace transform, such as finding Laplace transform using its definition and finding Laplace transform using derived table of formula. So if you haven't watched them yet, I will just also put the links on the description so you can check them first. So here we will just continue solving more problems in finding inverse Laplace transform. So in part 1, I think we have solved 20 problems. So we will just continue, and this time we will solve problems that involves partial fraction decomposition particularly. Okay, so here are the standard inverse Laplace transform formula that we must have or we must memorize. Okay, so these are derived from the standard Laplace transform of different function of t. Okay, so we have the first one, the inverse Laplace transform of 1 over s is 1. The inverse Laplace transform of n factorial over s raised to n plus 1 is t to the n. The inverse Laplace transform of 1 over s minus a is e to the at. The inverse Laplace transform of a over s squared plus a squared is sine 80. The inverse Laplace transform of s over s squared plus a squared is cosine 80. The inverse Laplace transform of a over s squared minus a squared is hyperbolic sine 80 or sinh 80. The inverse Laplace transform of s over s squared minus a squared equals hyperbolic cosine 80 or cos 80. And the inverse Laplace transform of gamma of alpha plus 1 over s raised to alpha plus 1 is equal to t raised to alpha. By the way, here alpha should be greater than negative 1, while here n should be whole numbers such as 0, 1, 2, and so on. Okay, so we will just use this formula again to evaluate the inverse Laplace transform. So, by the way, inverse Laplace transform has also linearity property. That is, if you have the inverse Laplace transform of sum of functions f of s, you can just get the sum of the inverse Laplace transform of each. Okay, applying the linearity property. So here are the problems that we have solved in part 1. So we solve until problem 20. Okay, so let's just continue. Let's have problem 21. Find the inverse Laplace transform of f of s given by 2s minus 6 over s squared plus 9. Okay, so getting the inverse Laplace transform of f of s, okay, we can have the inverse Laplace transform of the given function 2s minus 6 over s squared plus 9. So notice that we can distribute this s squared plus 9 on every term on the numerator, or what I mean is you can divide each term of the numerator by s squared plus 2. So doing that, we will have inverse Laplace transform of 2s over s squared plus 9, then minus 6, because it's negative 6, so I put minus here, over s squared plus 9. So since we have two terms here, these two rational expressions, you can distribute the inverse Laplace operator, applying linearity property. So we'll have inverse Laplace transform of 2s over s squared plus 9, then minus inverse Laplace transform of 6 over s squared plus 9. So here, on the first inverse Laplace transform, we can apply the inverse Laplace transform formula for s over s squared plus a squared, which is equal to cosine 80. Okay? So, we don't need this 2 here because it's just a constant. You can just put in front of the inverse Laplace operator. So, we have 2 inverse Laplace of s over s squared plus 9. So, if you pattern in the standard formula, okay, we have s, we have s squared, and then we have this a squared. Comparing it with the constant 9 here, you can rewrite 9 in a squared form, meaning in exponential form, having a base a and exponent of 2. 9 can be written as 3 squared, right? Therefore, the value of a here should be 3. Okay? So, a here is 3. Therefore, it's equal to 2 times the inverse Laplace of s over s squared plus 3 squared is equal to cosine 80. But the value of a is 3. You can substitute here in the cosine. We have cosine 80 or cosine 3t. So this is the inverse Laplace transform of the first term. How about the inverse Laplace transform of the second one? So this time we can apply the formula inverse Laplace transform of a over s squared plus 9 plus a squared, sorry. Okay. So here we have s squared and we have also a squared, but we can rewrite 9 as well as a squared form, which is 3 squared, right? Okay, 3 squared, so that the value of a here is 3 also. But notice in the formula that on the numerator we should have also the constant a. So we should have also 3 here so that we can apply this inverse Laplace transform formula. This, by the way, equivalent to, this is equal to sine 80. Okay? So going back, we should have a constant a on the numerator as well, which is 3. But notice that we have 6 on the numerator. We can factor that 6 as 3 times 2, right? So, therefore, we already have the 3 on the numerator, but we have an extra 2 here, which is another constant. You can just put it in front of the inverse Laplace operator because it's just a constant. Leaving 3 on the numerator because we need 3 on the inverse Laplace transform formula for sine. Okay? So, it is now equal. So, putting 2 in front of the inverse Laplace operator, we will have negative 2 times the inverse Laplace of 3 over s squared plus 3 squared. Therefore, we have negative 2. Inverse Laplace transform of this is sine 80, right? But a is 3, so we can substitute here 3. So, therefore, negative 2 sine 3t. So, finally, the inverse Laplace transform is 2 cosine 3t minus 2 sine 3t. Okay? Next, 22. Okay, for 22, what if we have f of s is equal to 1 over s squared plus as? Okay, a here is a constant. So notice that we don't have a standard inverse Laplace transform formula for this form. But we can factor out the denominator, common monomial factor of s squared and as is s, right? So you will have s times quantity s plus a as the factored form, applying common monomial factoring. So once you already have more than one factor, meaning at least two factors in the denominator, because we already have two factors, we have factor s, both linear factors, s and s plus a. we have two linear factors, that's the time that we can apply partial fraction decomposition. Okay, so whenever you have at least two factors in the denominator, you can always try to decompose into sum of partial fraction. So we will apply what we've learned from uh, partial fraction decomposition. So you also apply this partial fraction decomposition when integrating rational expressions, right? So another application of partial fraction decomposition is in inverse Laplace transform. So using partial fraction decomposition, or PFD for short, PFD. So we decompose this 1 over S times S plus A as a sum of partial fraction. So this is case 1. Remember, we have 4 cases in partial fraction decomposition. Okay, case 1 is when you have linear factors that are non-repeating. Okay, the highest exponent of the S here is 1. Okay, and there's no exponent or power for each linear factor that is at least 2. It should only be 1, right? So case 1, okay, non-repeating linear factors. So to decompose that as a sum of partial fraction, you'll just need to consider all the linear factors. You have the S and you have the S plus A. And since they are both linear factors, you can just put a constant, a known constant on their numerators. So usually we use capital letters of the alphabet. So for S, let's have A, capital A. And for S plus A, we have capital B. Okay, so the goal is to find the value of this A and B. So the next step is to multiply both sides of this equation by the LCD, which is always the original denominator, S times S plus A. So distributing S times S plus A, multiply both sides to each term. So for the for the left side, you can cancel all the factors here. We will be left only with the numerator always, which is 1. When you multiply the LCD by A over S, you can cancel out this S. Then we are left with A times S plus A plus, how about P over S plus A? If you multiply by the LCD, you can cancel out the S plus A. We are left with B times S. So we actually have two methods here. We can have equating coefficients or the cover-up method. Okay? So we can combine them, or you can just use only one method. Okay? So here in our video, there will be times that we will use equating coefficients and cover-up methods. So we will both use of them depending on the problem. So it's better to use here cover-up method if it's case 1. Okay? Because by cover-up method, okay, you will just need to assign value of S in order for you to solve a particular unknown. Let's say if you want to solve for A first. How do you find the value of S? In what value of S will you set this S to so that you can eliminate the A? So when you're considering the A, when you're trying to solve the unknown variable A first, look for the factors of the other variable, unknown variable, which is the B, right? This is the other unknown variable. Look for its factor, its S, right? Equate that factor to 0. So you should have S is equal to 0. Then solve for S. So it is already solved for S because S is equal to 0. So therefore, this is the value of S that that we will want to have in order for us to obtain the value of a. So set s to 0, and what will be the formula for a now? So setting s to 0, the formula for a is equal to the whatever is your term or whatever is the expression on the left side, which is 1. That will be the numerator over the coefficient of the a, which is s plus 9. So that will be the denominator. And then evaluate this expression at s to 0, equal to 0. Meaning you will substitute s is equal to 0 here. So it's equal to 1 over 0 plus 9. Sorry, it's not 9. Okay. No, no. It's not 9. It's a, right? Okay, a. I thought it's 9. But it's a. So if you set a to 0, if you set s to 0, you will have 1 over 0 plus a, or 1 over a. So this is the value of capital A, 1 over a. How about if you want to solve for b? So what value of s will we have? This time, since we're considering to solve for b, look for the factor of the other unknown, which is the capital A, right? Its factor is s plus 2. Equate that to 0. So s plus a is equal to 0. Then solve for s. So this time, you can transpose the a to the right side so that s is equal to negative a. So therefore, you will set s equal to negative a for you to be able to solve the b directly. So therefore, b is equivalent to, so whatever is the expression on the left side, which is again 1, that will be the numerator. Then over the coefficient of of p, which is s. But this is evaluated at s is equal to negative a. So you will substitute negative a to every s here. So therefore, b is equal to 1 over s, but replace s with negative a. So 1 over negative a, or negative 1 over a. So therefore, the value of capital A is 1 over a, and the value of capital B is negative 1 over a. Now, we can rewrite 1 over s times s plus a now in this sum of partial fraction form, substituting the values of the obtained capital A and capital B. So capital A is 1 over a, so you have 1 over a over s, plus capital B, it's negative 1 over a over s plus a. Okay? Because this form of the original expression, we can easily now find, from this form of the original expression, we can easily find the inverse Laplace transform. Okay? Applying linearity property. So therefore, the inverse Laplace transform of f of s, which is this one, is just the inverse Laplace transform of each. So applying linearity property, get the inverse Laplace transform of each. So if you have a constant for the first term, 1 over a is considered as a constant. We can just put it in front of the inverse Laplace operator. So 1 over a times inverse Laplace transform of 1 over s, right? Also this one, it's constant. The negative 1 over a is constant, so you can just put in front of the inverse Laplace operator. So you have negative 1 over a inverse Laplace transform of 1 over s plus a. So therefore, if we have 1 over a inverse Laplace transform of 1 over s, take note that's standard inverse Laplace transform formula equivalent to 1, right? Minus 1 over a inverse Laplace transform of 1 over s plus a. Again, we can apply the formula for the inverse Laplace transform of 1 over s minus a equal to e raised to 80. Okay? Where this is the value of a. But if you pattern here, from the original given, we have minus a here on the standard inverse Laplace transform formula, but we have plus a here. So what we can do is to rewrite this as negative of negative a, right? Because negative of negative a is the same as positive a. If you compare, the value of a here should be negative a. Okay? So the inverse Laplace transform of this is e raised to negative a then t. Okay, so this is the final answer. Or actually simplifying further, this times 1, 1 over a times 1 is just equal to 1 over a. Okay, so this is the final answer. Okay, next. 23. What if f of s is equal to 1 over s squared plus 3s? So what do you notice? It's almost the same on the previous problem. Right here, this is the previous problem. If we try to copy, comparing the two given, we have 1 over s squared 3s as. Therefore, if we assign the value of a here as equal to 3, we can also decompose this as a sum of partial fraction. If we try to factor this as 1 over s times s plus 3, okay, as a sum of partial fraction, it is, so since this is also the same case as in previous problem 22, it can be decomposed as a over s plus b over s plus 3. Okay, but if we try to copy the value of the capital A and capital B here, it takes the form for A is 1 over A, right? And for B is negative 1 over A. Comparing that the value of A from the given is 3, we should have capital A equal to 1 over A, which is 1/3. And for capital B, negative 1 over A, which is negative 1/3. So therefore, 1 over S times S plus 3 is equal to 1/3 over S plus negative 1/3 over S plus 3. Or actually, if you don't know this formula yet, okay, you can just do the same process as we did on previous problem. It's just that it's coincident that we already have this format of the denominator, s squared plus 3s. We already solved the form 1 over s squared plus as. So that's why I already used the derived formula on the previous problem. Okay? So therefore, if we try to get the inverse Laplace transform of f of s, this one, you can just get the inverse Laplace transform of its partial fraction. So 1/3, just put it in front of the inverse Laplace operator because it's just a constant. So 1/3 inverse Laplace transform of 1 over s. Also, this negative 1/3, put in front of the inverse Laplace operator. So you have negative 1/3 inverse Laplace transform of 1 over s plus 3. So 1/3 inverse Laplace transform of 1 over s, again, that's 1, minus 1/3 inverse Laplace transform of 1 over s plus 3. You can rewrite this as s minus negative 3, right? So that the value of a is negative 3. And then applying this inverse Laplace transform formula, we have e to the 80. Okay, so 1/3 e to the 80, replacing the value of a, which is negative 3, we have e to the negative 3t. Or 1/3 times 1, it's just 1. 1/3. So this is the final answer. 1/3 minus 1/3 e to the negative 3t. Okay, next, 24. 24. What if our f of s is s plus 2 over s squared minus 6s plus 8? Okay. So we have quadratic trinomial in s in the denominator. So we don't have a standard formula for this, but we can factor. So we have s plus 2 over factoring out s squared minus 6x plus 2 into product of two binomials, right? Factors of s squared is s and s. And think of the factors of 8 that when you add is equal to the coefficient of s, negative 6. We can have negative 2 and negative 4, right? Because negative 2 times negative 4, positive 8. Negative 2 plus negative 4, negative 6. So this is the factored form of s squared minus 6s plus 8. Notice that we also have two factors. So when we have, and again, when we have at least two linear factors or combination of linear or quadratic factors, at least two in the denominator, we can apply partial fraction decomposition. Okay, so by partial fraction decomposition, which is still case 1, non-repeating linear factor, s plus 2 over s minus 2 times s minus 4 can be decomposed as sum of partial fraction. So linear factors s minus 2, s minus 4. So you will have over s minus 2 plus over s minus 4. And then just put a known constant under numerator, let's say for s minus a, s minus 2 capital A, and for s minus 4 capital B. Then we multiply both sides by the LCD, which is the original denominator, s minus 2 times s minus 4. So multiply the left side by the LCD, everything will cancel out. Therefore, we are left with just the numerator, s plus 2. Multiplying the LCD by a over s minus 2, cancel out the s minus 2. We have a times s minus 4. Then lastly, multiply b over s minus 4 by the LCD, cancel out the s minus 4. We have b times s minus 2. Now, by cover-up method, again, if we want to solve for a first, so we set s be equal to, so look for the factor of the other unknown b. Its factor is s minus 2, right? You set that to 0. Solve for s. S is equal, transpose negative 2 to the right, positive 2. So s is equal to 2. So if we set s equal to 2, we can directly find the value of a equal to the left side, which is s plus 2. That will be the numerator. Then over the coefficient of a here, which is s minus 4, that will be the denominator. And this expression is evaluated at 2. So we will replace every s with 2. So doing that, we will have 2 plus 2 over 2 minus 4. Or 2 plus 2 is 4 over 2 minus 4, negative 2. 4 divided by negative 2 is negative 2. Okay. So, next is to solve for b. So, this time, we can set s equal to what? So, since we're solving for b now, look at the factors of the other unknown, capital A. Its factor is s minus 4, right? So, set that s minus 4 to 0, then solve for s. So, transpose negative 4 to the right, s is 4. So, therefore, you will set s equal to 4 to find the direct value of b equal, again, to the left side, s plus 2, that will be the numerator, over the factor of b, s minus 2. That's the denominator. Then evaluated at s is equal to 4. Okay, so we will replace this time every s here with 4. So we will have 4 plus 2 over 4 minus 2. 4 plus 2, that's 6. Over 4 minus 2, that's 2. So 6 divided by 2 is 3. So therefore, the value of b is positive 3. Okay, now that we have a and b, we can go back to this sum of partial fraction if we copy. Okay, we can now replace the values of a and b with the obtained values. For a, it's negative 2. Replace it with negative 2. And for b, it's positive 3. We can replace this with positive 3. So, getting the inverse Laplace transform of f of s, which is this original expression, which is now equivalent to this sum of partial fraction, you can just get the inverse Laplace transform of each. So, put this negative 2 constant in front of the inverse Laplace transform operator, then times 1 over s minus 2, inverse Laplace transform of 1 over s minus 2, plus 3 times inverse Laplace transform of 1 over s minus 4. So we can apply the standard inverse Laplace transform again, formula for this one. Okay. 1 over s minus a, its inverse Laplace transform is e raised to 80. So we need to find the a. So a here in the first inverse Laplace transform is 2. While here on the second term, a is equal to 4. So we have negative 2, inverse Laplace transform of 1 over s minus 2 is e raised to 80. Therefore, we have e raised to 2t. Then plus 3, inverse Laplace transform of 1 over s minus 4 is e raised to 80. Therefore, we have e raised to 4t. So this is the final answer. Okay, next. 25. What if f of s is equal to s plus 1 over s squared minus 4s? Okay, we factor the denominator. Common monomial factoring, we have s times s minus 4. So applying partial fraction decomposition, since we have two linear factors. So s plus 1 over s times s minus 4 is equal to, considering the two linear factors, we have over s and s minus 4. Then put unknown constants on their numerator. Let's have capital A and capital B. Okay, multiplying both sides by the LCD, which is the original denominator, s times s minus 4. Multiplying the LCD by the left side, canceling out every factor, we are left with the numerator s plus 1. Multiply a over s by the LCD, cancel out the s, we are left with a times s minus 4. How about b over s minus 4, multiply by the LCD, cancel out the s minus 4, we are left with b times s. Okay, by cover up method again, if you want to solve for a first, set s to what? So look at the factors of b, which is s, equated to 0. Solve for s, therefore, it's already solved for s, which is equal to 0. So set s equal to 0 so that the value of a is equal to the expression on the left side, s plus a, divided by the coefficient of a, which is s minus 4. And evaluate this expression at s is equal to 0. So substitute every s here with 0. So we have 0 plus 1 over 0 minus 4, or 1 over negative 4, or negative 1/4. So the value of A is negative 1/4. And then to solve for B, this time we set S to, so if we're trying to solve for B now, equate the factor of the other unknown, capital A, which is S minus 4 to 0, then solve for X. So S minus 4 is equal to 0, therefore S is equal to, transpose negative 4 to the right, it will become positive 4. So S is positive 4. So set S equal to 4, then we can find B equal to the expression on the left side, S plus 1, over its coefficient S, and evaluate this expression at S is equal to 4. Substitute every S here with 4. We have 4 plus 1 over 4. So we have, okay, the value of B, which is 5 over 4. Okay. So replacing the values of A and B here in the partial fraction, let's copy. So A is equal to negative 1/4, substitute, while B is equal to positive 5 over 4, substitute. And then get the inverse Laplace transform of both sides. So we have to get the inverse Laplace transform of each term. So negative 1/4 inverse Laplace transform of 1 over S plus 5/4 inverse Laplace transform of 1 over S minus 4. So negative 1/4, we know that the inverse Laplace transform of 1 over S is 1, right? Plus 5 over 4, inverse Laplace transform of 1 over S minus 4 is e raised to 80 again, but A is equal to 4. So replace A with 4 here, we have e raised to 40. And then multiplying negative 4 times 1, it's just negative. Negative 1/4 times 1, it's just negative 1/4. So the final answer is negative 1/4 plus 5/4 e raised to 40. Okay, next. 26. What if f of s is equal to 2s squared plus 5s minus 4 divided by s cubed plus s squared minus 2s? So let's factor first the denominator. So copy the numerator. We can apply common monomial factoring first. Factor out the common monomial factor s. So we have s times s squared plus s minus 2. And we can still factor out s squared plus s minus 2, right? So we have 2s squared plus 5s minus 4 over s times, so factors of s squared is s times s. Then think of factors of negative 2. When you add is equal to the coefficient of s, which is positive 1. It can be negative 1 and positive 2. Because negative 1 times 2 is negative 2 and negative 1 plus 2 is positive 1. So therefore, this is the factored form of the denominator of f of s. So since we have three factors, linear factors in the denominator, we can apply partial fraction decomposition. So by partial fraction decomposition, again, it's case 1 because we have linear factors only that are not repeating. So we have 2s squared plus 5s minus 4 over s times s minus 1, s plus 2. So consider each factor. So we have over s minus 1, and over s plus 2. And just put any unknown constant variable on the numerator. Let's have capital A, capital B, and capital C. So next is we multiply both sides by the LCD, which is the original denominator, s times s minus 1 times s plus 2. So if we multiply the left side by the LCD, we can cancel out everything. Therefore, we just have the numerator 2s squared plus 5s minus 4. For a over s, we can cancel out the s. We just have a times s minus 1 times s plus 2. For b over s minus 1 multiplied by the LCD, we can cancel out s minus 1. We have b times s and s plus 2. Okay. Then last, multiply the LCD by c over s plus 2. Cancel out s plus 2. We have c times s minus 1. Okay. So by cover-up method, set s be equal to, so if you want to solve for a first, what if we already have three unknowns? Capital A, capital B, capital C. So consider, if you're trying to solve for A, consider the common factors in the other two variables, B and C. Do they have common factors? Yes. S, right? So set that common factor to 0. Set S to 0, solve for S. It's already equal to 0, right? So when we set S equal to 0, we can directly solve for A equal to the expression on the left side, which is 2s squared plus 5s minus 4, then over the coefficient of A, which is s minus 1 times s plus 2. But this is evaluated at s is 0. So we will replace every s with 0 here. So A is equal to 2 times 0 square plus 5 times 0 minus 4 over 0 minus 1 times 0 plus 2. So this will be 0. We just have negative 4 over 0 minus 1, it's negative 1 times 0 plus 2, 2. So negative 1 times 2, it's negative 2. So negative 4 divided by negative 2, it's positive 2. So we already have values of A. Next, if we want to solve for B, what value of S can we have? This time, look for the common factor of the other two variables except B. So look for the common factors of A and C. Obviously, it's S minus 1, right? So set that to 0. Set S minus 1 equal to 0. Then solve for S. Transpose negative 1 to the right. S is positive 1. So when we set S equal to 1, we can directly solve for B equal to the expression on the left side. Okay, copy. Then divided by the coefficient of B, S times S plus 2. And evaluate this expression at S. Sorry, there's no S. Set S equal to 1. Okay. Evaluate this at S is equal to 1, meaning replace every S here with 1. So we'll have 2 1 square plus 5 times 1 minus 4 over 1 times 1 plus 2. Okay, so we will have 2 times 1 square plus 5 times 1 minus 4. That's 7 minus 4 or 3 over 1 times 1 plus 2, 3. So 1 times 3, it's 3. 3 divided by 3 is 1. So the value of B is 1. Then lastly, to solve for C, we can set S equal to what? So we're trying to solve for C now. This time, we can look for the common factor of the other unknown, A and B. What is the common factor of A and B? The linear factor S plus 2, right? Equate that common factor to 0. So S plus 2 equate to 0, then solve for S. Transpose 2 to the right, S is negative 2. So we can set S equal to negative 2 to obtain the value of C. Again, equal to the left side. Expression on the left side, copy. That will be the numerator. Then over the coefficient of C here, which is S times S minus 1. Then evaluate this at S is equal to negative 2. Replace every S with negative 2. So we have 2 times negative 2 square plus 5 times negative 2 minus 4 divided by negative 2 times negative 2 minus 1. Okay. If we simplify, 2 times negative 2 square plus 5 times negative 2 minus 4. So this is 4 times 2, 8 plus negative 10, negative 2 minus 4, negative 6 over negative 2 times negative 2 minus 1, negative 3. Negative 2 times negative 3, positive 6. So negative 6 divided by 6, negative 1. So therefore, the value of C is negative 1. Okay, now that we have all the unknown constants on the numerators, A, B, C, we can substitute here in the sum of partial fraction. Let's copy. Okay, substitute the value of A, which is positive 2. Okay, you have positive 2 here. Value of B, substitute with 1. Okay. Then, last, value of C, substitute with negative 1. Okay. So, if we try to get the inverse Laplace transform of f of s, which is this original expression, just get the inverse Laplace transform of each. So, we have 2 times inverse Laplace transform of 1 over s plus inverse Laplace transform of 1 over s minus 1. So since we have negative 1 here, we should have minus inverse Laplace transform of 1 over s plus 2. So 2 times the inverse Laplace of 1 over s is 1 plus, so inverse Laplace of 1 over s minus 2, so that's e raised to at. But the value of a here is 1. So replace a here with 1, it's e raised to 1t or simply e raised to t. Then minus, again, identify the a here. So s plus 1 can be written as s minus 2. I mean s plus 2 can be written as s minus negative 2, so that the value of a is negative 2. So its inverse Laplace transform is e raised to at, and substitute a, which is negative 2, it's e to the negative 2t. So simplify 2 times 1, it's just 2. So this is the final answer. 2 plus e raised to t minus e to the negative 2t. Okay, next. Number 27. What if f of s is equal to s over s squared plus 2s minus 3? So you factor first the denominator. Factor of s squared is s times s. Factors of negative 3 when you add is positive 2, negative 1, and positive 3. Okay. So get the partial fraction decomposition since we have two linear factors. So s over s minus 1 times s plus 3. Again, it's still case 1, non-repeating linear factors. consider each factor. So, over s minus 1 and over s plus 3. Then put unknown constant on the numerator, let's say capital A and capital B. Then multiply by the LCD both sides, so s minus 1 plus s times s plus 3, which is the original denominator. So distribute, multiply the left side by the LCD, you can cancel out every factor. We are left with s. Then for a over s minus 1, cancel out s minus 1. We have a times s plus 3. Then for b over s plus 3, cancel out the s plus 3. We have b times s minus 1. Okay, by cover-up method, if we want to solve for a first, we can set s equal to, look at the factor of the other unknown constant b, which is s minus 1. Equate that to 0. S minus 1 is equal to 0. Solving for s is 1, right? So if we set s to 1, a is equal to the left side s, that's the numerator, over the denominator, which is the coefficient of a, s plus 3. Then this is evaluated at s is 1. So replace every s here with 1. You have 1 over 1 plus 3. Or 1 over 1 plus 3, that's 1/4. Next, to solve for b, set s be equal to, this time, look for the factor of the other unknown a. Its linear factor is s plus 3, right? Equate it to 0. Then solve for s. Therefore, s is negative 3. So set s equal to negative 3 so that the value of b is the expression on the left side, s, over the coefficient of b, s minus 1, then evaluated at s is equal to negative 3. So replace s with negative 3. So negative 3 over negative 3 minus 1. Negative 3 over negative 3 minus 1, negative 4. So negative 3 divided by negative 4, positive 3/4. So we already have a and b. Replace the values here in the partial fraction. Okay. A is equal to 1/4 and b is equal to 3/4. Okay, getting the inverse Laplace transform of f of s, this original given, it is equal to the inverse Laplace transform of each term. So we have 1/4 inverse Laplace of 1 over s minus 1, then plus 3/4 inverse Laplace of 1 over s plus 3. So 1/4 inverse Laplace transform of 1 over s minus 1 is e raised to the at, where a is equal to 1. So therefore, e raised to 1t or e raised to t. Next, plus 3/4 inverse Laplace of 1 over s plus 3. So that's e raised to at again. But the value of a here is negative 3. So just get the opposite sign of the constant. Okay? So we will have e raised to negative 3t. So this is the final answer. Okay. 1/4 e to the t plus 3/4 e to the negative 3t. Okay, so I think that's it for this part 2. So we can still have part 3. So stay tuned for part 3. We will still solve other problems more on finding inverse Laplace transform using partial fraction decomposition. Okay, so I hope you learned something from this video. So don't forget to subscribe to our YouTube channel and click the notification bell so that you will be updated whenever we have new uploaded videos and upcoming lessons. And also, all the past live streams for this subject, Advanced Engineering Mathematics, are just linked on the description. So if you're interested to watch, you can just check the description as well as the actual playlist for the Advanced Engineering Mathematics subject. I will just also put the link on the description. So good luck to your studies or on your subject in Advanced Engineering Mathematics. Okay? And I hope you will pass your subject. So just solve as many problems as you can, and you will be good at uh, the topics, particularly here in Laplace transform. Okay, so see you on my next live. Thank you for watching. Bye bye.